Okay, let's get started. Let me hit the lights. All right, we'll go with that. Today, we are going to start our last data structure. This will be the last one that we're going to do. So we're getting near the end. We are going to spend a couple days on this last data structure, which is hash tables. We'll spend 3 days on them. The plan is to go over how they work. So we're going to take a look at that today. And then we're going to look at a couple examples of how they are used in actual programs. So I know we've looked at some other programs before. I think we looked at Meld and some games that I worked on in the past. We will look at a couple more examples of that to give you guys a practical application for hash tables, because these are very common, these are used very often, and they are different from any of the ones that we've done in the past. Okay, so we're going to mix it up a little bit with this last one. Okay, any questions? Okay, well, let's get started. If you go to Canvas, under modules, you'll see there's a few files there. Currently, we'll add more to this as we go through. So as we create these videos, we'll put these up there as well. All of the ones for binary search tree are now up there, because I think your program is due tomorrow?
Next week.
Next week. Good luck with that. So make sure you get that turned in. The last video does have some of the stuff that we talked about specific to what you needed to do for your third programming project. So make sure you check that out if you weren't in class. Make sure you run through that video to make sure that what you did is correct. Bless you. Okay? All right, well, let's get started with hash tables. I'm going to download a couple different things. The first is, let's take a look at this PowerPoint. And I know I don't typically do PowerPoints, but we're going to look at one today. Okay? I did not create this. I don't know who did. Sweet graphics. Awesome color palette. Strong, bold colors that you can't read. I'm looking at the video. Get excited. All right, so let's talk about hash tables. We have discussed several times the concept of a base data structure. Who remembers what a base data structure is? Strong showing. Right here.
A structure that you use to build other structures.
Very good. So it's a structure that is independently functional. You can use it as is, or you can use it to build more advanced data structures. All right. Examples that we have used so far this year: arrays. Arrays work by themselves. You can use an array as is. You can also use an array as a base data structure to implement more advanced data structure, like a heap. Okay, same thing with a linked list. You can use a regular linked list, or you can use it to implement a stack or a queue or something like that. Okay. And so we're going to take this idea of a base data structure and we're going to apply it to hash tables as well. And so if you look up here, you can probably figure out that we are going to use arrays again as the base data structure for implementing our hash table. Okay. Now, one thing I will tell you, which is confusing, is depending on the language, hash tables are called different things. Okay. You might also hear them referred to as dictionaries. Same thing. Good so far? I don't even know what they're called in Java. Do you know what they're called?
No idea. I think Google is
Google. So neither your teacher nor your TA knows what they're actually called in the language that we're using. Let's look. All right, so it looks like they're called hash table. They might have both. Yep. But not for 8, just for 7. They're pretty interchangeable. I know, I use them in C# frequently, and they're called dictionaries there. But maybe hash table is like an old word. I have no idea. You need to know both. Hash table, dictionary, too. So the idea here is that we're going to use an array that acts as our base data structure. Okay? In this example, we have an array of 701 elements. It goes from 0 to 700, so there's a total of 701. Let's talk about a couple terms. So, you guys know in most of the data structures we've talked about, a lot of times we need to keep track of specific pieces of information in order to make that data structure work. Okay, so for example, if we're doing a binary search tree, one of the things that we have to keep track of is a reference to a left child and a right child. Okay, if we're using a stack or a queue and we're using a linked list implementation, we have to keep track of the object that's next in the list. We have to keep that next reference. Okay? So a lot of times when you are implementing a structure into your program, you might have to add or modify the pieces of information that your objects keep track of in order to make those objects usable in a specific structure. What we see in the case for hash tables is this idea called a key. A key is simply a value that is unique to that object. No other object can have the same value for that key. This can be just about anything. It can even be a combination of two things. So common things that we're probably familiar with, Social Security numbers are unique. No other person in the United States has your Social Security number. Let's hope at least. Okay. Got some issues if that's the case. Your student ID number here. Okay, so everyone's got an 800 number. That's unique. No one else that's currently enrolled has your 800 number. All right. That's the basis. So when you go for advising or you go to do anything through Banner, first thing you do is you type in your 800 number that pulls up all of your accounts. Okay? That would be your key. If we're running an inventory system, it could be something like some product ID number that we come up with. No other product that we sell in the store has that same ID. And I mentioned it could also be a combination of two things. I've used a situation in the past. Did we look at Mel, that game? The puzzle with the dragon, the colors, and you guys looked at me like, what? Picture a grid.
We did it jumping over the T.
Jumping over the T?
Yeah.
The sugar cube that was trying to escape getting dumped in the pool.
Oh, okay. We didn't look at Mel. Did we look? It's a space puzzle game where you're dragging colors.
Sounds cool.
You can show us.
It sounds a lot cooler than it is. The game's fun. It's if you like puzzle games. Everybody knows what I mean by grid? Yes. If we are talking about each tile in a grid or each square in a grid, if we wanted to put each of those into a hash table, which I did in Mel, the key for each tile or each node in the grid could be a combination of their row and column. Okay? Multiply by the row, add the column. That would give you a unique value that no other would have. It's like if you numbered it 1, 2, 3, 4, 5, 6. You get that by multiplying the row, adding the column. Anyways, multiplying by the number of rows and adding the column as well. long story short, every object that you want to put into the hash table has to have a unique value that we'll call the key. All right, so if we've got an example here. We've got a hash table. We have an array, 701 elements, and we're going to put people in there. And so what we have is we have this apparently random string of 9 numbers. That was confusing. Not a string of 9 numbers, but a set of 9 numbers. Okay? That will act as the key. So the idea here is we use the key, we use this unique value as the basis for where we put the objects in the hash table. Now, one of the things that you'll immediately see is strange is the fact that we have holes in the table. This is normal, and you can expect this to happen. When you place an object in the hash table, it's placed based off of its key, but not based off of how that key relates to other keys that are already in the table. Okay? So it's not like if this number is less than this number, he's going to appear earlier or in an index that is lower. Okay? It doesn't work like that. And we don't put them in some sort of first in, first out, or last in, first out order like we did with stacks and keys. When we put an object in there, that key isn't compared to any other key that's in there. Okay? So it works a little bit different from what we're used to. So expect to see blank spots in your hash table. All right. So when we put an object into the hash table, if its key isn't compared to something else, or we don't put it in any sort of ordering, then how do we determine where exactly we put it in? Well, here's how this works. Okay? We know we're going to take that key. We know that the key is a unique number. And the idea here is we're going to take that key and we're going to convert it to an index. Okay? We take that key, we take their social security number or whatever that number means, and we're going to convert it to an index, and that index has to be a value between 0 and 700. Does that make sense? Good so far? All right. Now, the process of taking a key and converting it into an index is called hashing. And that's where the hash table comes from. The method or the function that takes that key and converts it to an index is called a hash function. So here's the process. We have a key, unique identifier for an object. We take the key, we pass it to the hash function. The hash function returns the index where we should put that object. Okay, let me say that again because this is important. We have an object that we want to add to the hash table. Okay? We take that object's key, we take that object's unique identifier, and pass it to the hash function. The hash function does magic and returns the index of where we should put that object in the array. Questions on that? That's kind of what's explained here. The hash value is the index where we should put it. Now, the difficult part with implementing hash tables is coming up with a good hash function. And the better your hash function, the better your performance will be out of your table. Okay? Now, there are some generic ones. There are some generic hash functions that can be used. And these give you decent results. But as we kind of go through it, we're going to see some of the limitations of them. Okay. So this generic one is the only one that you guys need to know for this course. Okay? A lot of times what you get into are very specific hash functions that are tailored for a particular program or a particular solution. Okay, so a lot of times, depending on the object that you're going to put into the hash table, depending on its characteristics, and depending on what you are using as its key, the hash function that you write is going to be different. So what you end up with a lot of times, especially in my experience, you write custom hash functions based off of what you're putting in the hash table. Okay, so it doesn't do us a whole lot of good to cover a variety of hash functions because they are so specific to what it is that you're doing. I could teach you 10 and you could never use any of them. Okay, because you might implement hash tables every other day and go 3 years before repeating one. Okay? It just depends on what you're putting in. Now, with that said, there are some generic ones, and this is a generic one. Okay? And you do need to know this one. This is called the division method. Okay, the division method. You need to know that because I'm going to call it by that name. Okay? This is the division method. And what it does is it compresses a value down into a specific range. It's going to compress a value down into a specific range. So the division method is a compression function. It compresses a number. Now the formula for the division method is very simple. It's key, which is unique identifier, key mod size. Key mod size. That's the formula. So you take whatever that object's unique identifier is. In this case, it's the number 580-625-685. That's this baby with really yellow hair. Looks like he might be out of Chernobyl. That's his key. That's his unique identifier. So we take that key mod division. This is remainder division. Everybody know what mod is? Anybody not know what mod is? Very good. Key mod 701. Now, this comes from the length of the array. The index number to the last element in the array is 700, but we know arrays start with 0. So the total number of spots in the array is 701. Okay? Key mod size. Questions on that? So if our array had 462 elements, we would have this mod 462. Okay? Now, what's 580,625,685 mod 701? Anybody know off the top of their head?
4.
Jameis did it in his head. That's why he's your TA. So close. It's 3. Google's the calculator. Now, anybody know what the maximum value we could get by doing mod 701? Take any number in the world, mod 701. What's the max value you could get?
700.
700, correct. Now, even if we did like 40 trillion mod 701, or even if we did 1 mod 701, we're always going to get a value in the range of 0 to 700. That's the way mod division works. It's a remainder. The maximum value we can get is whatever you are dividing by minus 1. Okay? Because again, it returns what is left over. And if you have a value that is left over larger than 701, well then that value could have gone into 701 one more time. Right? Does that make sense? Like if you have a pizza, we'll go back to 3rd grade when you learn fractions. You guys learn fractions in 3rd grade? Kindergarten? Must have been on the advanced track. You got a pizza, and you're going to divide it up between 3 friends. Okay? what is the maximum number of pieces that you can have left over that aren't equally divided among your 3 friends? 2. Okay.
You love to ask.
You know what I was getting at. Okay. The maximum number of pieces that you can have left over, it doesn't matter how many pieces you have to start with, the maximum number of pieces you can have left over is going to be 2. So give you 1, give you 1, give you 1. Equal. Give you 1, give you 1, give you 1. That's equal. The maximum number of pieces that we can have without each person getting one of them would be 2. It's possible we have 1 left over. It's possible we have none left over. It's possible we have 2 left over. But if we had more than 2 left over, then we could give everybody 1 more piece. Okay? So when we're talking about looking at what is left over after we divide something among a certain number, the maximum number of leftover value is always what you were dividing by minus 1. If we're dividing pizza equally among 3 people, the maximum number of leftover pieces we can have that isn't equally divisible is 2. We're dividing by 3 minus 1. If we're dividing pizza among 701 people, the maximum number of pieces that we can have left over that isn't equally divisible among 701 people would be 700. Because if we had 701, then everybody could get 1 more piece. Okay, see how that works? So what we are doing when we divide by 701, we're looking at the remainder when we divide by 701, is we are effectively compressing this number into the range of 0 to 700. Which happens to correspond exactly to the index range of our array. Okay. Does this make sense? You guys seeing the connection here? Okay. So, we're trying to figure out where to put our radioactive baby. We're going to use the division method, so we take key mod size, and we said that that gives us a value of 3. So that tells us that our baby is going to get put here. Right, does that make sense? Again, take the key, pass it to the hash function. We're using the division method as our hash function. Hash function returns the index where we should put it, which is 3. Okay. So he goes here. All right? Good? Then we got JFK. His key is, I know it's hard to see, 701, 466, 868. Mod 701 gives us the value of 2. Uh-oh. Can we put him here? No. This is where we come into some issues. Term you need to know. When you attempt to put an object into an element of the array that already has an object, it's called collision. Okay? We wanted to put JFK in spot 2, but we couldn't because Lincoln was there already. This is called collision. It's not good. There are 2 different ways to handle collision. Well, we're going to look at 2 different ways to handle collision. There are other ways to handle it. Now, what it's describing here is the first way. And when we look at the 2 different ways, there's an easy way, and then there's a good way. First way that we're going to look at is the easy way. This is called open addressing using linear probing, which is a really fancy term that means keep looking until you find the next open spot. So again, we hit collision. We tried to put JFK in spot 2. We couldn't because Lincoln is there. So if we are using open addressing to find or to handle our collision, here's how this works. Again, this is called open addressing, or looking for the next open memory address, using linear probing, which means looking down the line. So we're looking down the line, or probing linearly, looking for the next open address, or the next open element in our array. Okay, so we do this one at a time. So we start at where we wanted to put him. Can't put him there. So now we're going to look at the next position. Well, can we put him here? No. Can we put him here? No. Can we put him here? Yes. Okay, so we will instead put him in spot 5. Now, what was the cost of that? What did that cost? How many operations was that? 1, 2, 3, 4. We're comparing. We were checking, is this empty? No. Is this empty? No. Is this empty? No. Is this empty? Yes. So we got 4 operations. Best case scenario, what's the performance of adding an object to a hash table? Best case scenario. 01. Yep. Costs 1 operation. But remember, the 01 doesn't mean it costs 1 operation. It means that the number of operations is not affected by the size of our array. Specifically, the number of objects that are in the array. Best case performance, best case scenario performance out of a hash table for adding is 01. When you have no collision, you get 01. That's good. What's the worst case? Worst case scenario, what does it cost to add an object to a hash table? ON. Very good. Where you have to search or perform operations equal to the number of objects in the structure. So if it's full, or if it's full minus 1, you have just 1 spot left, the maximum number of spots you have to search is the entire array. Okay? For example, if we want to put an object in index 1, and the only open index is 0, then we have to check, are you open, are you open, are you open, and go all the way through, and then when we get to the end, we come back and start at the beginning, and check it. So, best case scenario, 01. Worst case scenario, ON. How you handle collision and how well you write a hash function will determine how close to 01 you get and how close to ON you get. Okay? This is really the first structure that we have looked at where there's a big swing between the two. I guess binary search trees kind of have that with, depending on whether your middle value is at the root or not, you get a nice balanced tree. But kind of the same thing here. Any questions so far with this? Okay, so the first method for handling collision is open addressing using linear probing. You keep going, keep going, keep going until you find the next open spot, and then you're going to put it there. Okay? But before we look at the second method for handling collision, we need to kind of look at what implications our first method is going to have on for when we go to try to find that object later on. Okay? So, most of the data structures that we looked at the beginning of the year, I specifically said, don't search them. Stacks, queues, linked lists, heaps. Those aren't good structures for searching. Okay, in fact, the cost to search all of those was ON, which is not good. Okay? Then we got into binary search trees, and their name indicates you should search them. Remember what the cost to search a binary search tree was? Close.
Log in.
Log n, very good. So log base 2 of n, where n is the number of objects in the tree, is the number of operations it takes to search or find something in the tree, which is good. Okay, if you have 256 objects, it's going to take you 8 operations. You can go up to 512 or 9 operations. You can have over 1,000 objects in the tree and find it with just 10 operations, worst case scenario. Okay? So this has really good growth. Hash tables are another example of a structure that is useful when you need to search frequently. You're searching your structure for a particular value. Now, based off of what we know so far, what can you tell me would be the best case scenario search for a hash table? O1. Good. For example, let's say we're searching for our yellow-haired baby. What value do you think we would need in order to find him? Good. Okay, we need the key. We need that unique identifier. It's like when you guys go to log into Banner, or you go to your advisor, and they say, what's your 800 number? Type in the 800 number, hit a button, it pulls up your information. It's exactly what happens here. We take this key, we take the baby's, whatever that value is, 580-625-685. We take that value, we pass it to the hash function. What's the hash function give us? Gives us an index. Good. That index tells us where we should expect to find that baby. So we take the key, pass it to the hash function. The hash function says 3. So we look, and it's right there. Took one operation. Again, it doesn't matter whether there was 1 or a billion objects in our hash table. We took the key, passed it to the hash function, it gave us 3. End of story. That's O1 searching. That's really good. That's the reason that hash tables are used so frequently. Okay? Now, what about JFK? Type in his key, pass it to the hash function. The hash function gives us what value? 2. So that's where he should be. He should be at 2. So we go to 2, and what we do is we compare the key, the value we typed in, JFK's key, to the object at position 2's key. And we see that they don't match. And what that tells us is, obviously, JFK is not at spot 2. So as the programmer, we know the method that we used for collision was open addressing. So what are we going to do? Does your key match? No. Does your key match? No. Does your key match? Yes. I found you. Okay. So again, our search took 1, 2, 3, 4 operations to find it. It's just an example. It says 701 elements, and it took 4 operations to find it. Now, it could have taken 700 or 701, but it didn't. It could have also only taken 1. Think for a second here. What can you tell me about the relationship between the size of the array and the likelihood that collision occurs? Think about this for a second. What can you tell me about the size of the array and its relationship on the likelihood that collision occurs?
I was just thinking when you were giving the number about moving over, that if you were at space 700, what you do is you got to the DNA, you had to move over 1. So I was thinking that the more you get, the more likely you are to get collisions. Like more spaces get filled in.
Good, good. So let me answer your first question. So the first question he had was, what happens if you get to the end? If you're in spot 700 and it's filled, and you can't go to 701 because it doesn't exist, you go back to the beginning at 0, and then you go from there. And to your second point, you're right. The more spaces there are, and the more spaces is a direct indication of how big your array is. So the larger your array, the less likely collision is going to occur. And when collision does occur, it reduces the number of spots you have to go until you find an open spot. Okay? So in terms of collision and in terms of collision handling, larger arrays are better. Okay, because larger arrays reduce the likelihood that collision occurs, and larger arrays reduce the number of spots you have to check until you find an open one. Does this make sense? What's the downside to large arrays? More expensive. You accept more memory. Again, you guys at this point should be familiar with the trade-off. Memory, performance. Memory, performance. The more memory something takes up, typically the better performance you're going to get out of it. The less memory something takes up, the worse the performance is going to be. Now, there's no magic number that says, if you're trying to figure out, well, I think we're going to have about 500 objects. If you're setting up an inventory for a store and you want to use a hash table, you think, well, I think I'm going to have about 500 objects that we're going to sell. We're going to have 500 different SKUs in our store. How big should I make my array? There's no magic number, okay, because it scales. You could say, well, let's make it 20% larger. Okay, so let's make it, we'll have an array of 600 elements. If we know we're only going to put 500 in there, let's have 600 so we know there's going to be some spaces. Okay? But you can't simply take 20% and apply it across the board. Because if you have, all of a sudden, well, let's write a program to keep track of all the students at UNC Charlotte as well. How many students here? 25? 28? 1,000? Not literally 25. And 20% on that, all of a sudden, now we've got a huge array. 5,000 blank elements. It's kind of big. So, I am less interested in you coming up with a good number for the maximum or for the extra space that you want to come up with. And I'm more interested in you simply understanding the relationship between increasing the size of the array, decreasing the likelihood of collision, and decreasing the number of spots you have to check before you find it. Okay? Does that make sense? Let's go. Let's go back to Canvas. And I've got this Excel document that I want to take a look at. And we'll probably wrap up with this. I'll make this bigger so you can see it in a second. I know we haven't covered the second method for handling collision, but in an effort not to talk to you for an hour straight, we're going to kind of move things around just a little bit. Okay, so we'll probably finish up with this, and then next class we'll get into the second method for handling collision because it's a little bit more involved. It works a lot better. But we'll get to it just a little bit. All right, so what we've got here is just a really simple Excel file. And if you look, I can make this bigger. What we've got here is just a value for the size. And then we have a series of entries. Okay? We have a key here, and it's hard to see. Let me explain what all of these values are. So, in this Excel file, there's a series of student ID numbers. 800 numbers, and all I do is they are random values. It's a random value between 800, 0000, and 800, 999, 999. So basically all of the different ranges any student can have as far as number. Each cell is randomly generated. Okay, and we can re-randomize it just by pressing a button. And we're re-randomizing the entire thing. Okay? Now, next to each key, and I don't know how many of these there are. It looks like there's 50, so 47 times 1, 2, 3, 4, 5, 6. So that's 50 times 6. Yeah, it's just close to 300. Okay. Close to 300 different objects that we are putting in there. Okay. And as you can see up at the top, our array size is 500. Okay, so we're putting roughly 300 objects into an array of size 500. So we have some leeways. We have some room for where we can put them. Okay? And then if you notice, we take a look at this example right here. This is in cell B4, and right next to it shows its index. We're using the compression method, the division method, where we're going to take that 800 number and we're going to compress it down into a value between 0 and 499, because that's the size of our array. So we use the built-in mod function where we are doing B4, which is the key, mod H1, which is the size. Okay? So this gives us an index of 455. So if we had an object, we had an actual student whose 800 number was 800, 653, 9 something 5, they would go and index 455. Same thing here. If your 800 number was 800, 080, 056, you would go and index 56. Does this make sense, how this works? Any questions on this? All right. Now you'll see obviously that some of these show up in red. This is because we've got conditional formatting applied to the Excel file that highlights in red any duplicate entries. Hence, collision. Okay? Now the purpose of this is simply to highlight to you the relationship between collision and the size of the array. Now, can you still see the colors? Can you see the reds? Now, you already know that the numbers are random. Watch what happens as I decrease the size of the array. See the number of red? Those are all of the collisions. As I decrease it, that value gets larger. Now, not a big change between 300 and 400 and 500. What if I double the initial size to 1,000? Less red? Okay. Now, because these are random, it's possible that we get duplicates. Okay. I'll make it 2,000. No collision. One collision. But the amount of red that we see directly relates to the size. Okay? You can mess around with this. You can download this directly from Canvas. All right, but hopefully this kind of illustrates that point a little bit. All right? Questions from me so far? All right, so here's what I want you to take away from part 1 of hash tables. Objects that we want to put in the hash table have to have a key. A key is simply a unique identifier. Okay? Can a key be a string? Could you do key mod size if it were a string?
Yes.
Can you convert a string to a number?
Sure.
Can you convert anything to a number?
Yes.
Everything in a computer breaks down to a 0 or a 1.
Yeah.
So a key can be anything as long as it's unique to that object. No other object in the hash table has that same value. Okay, so that's the first thing. Second, we're going to use an index structure as the base data structure for our hash table. We picked an array because that's what's easiest. Okay? Any index structure would work though. So as long as you access objects using an index number, like you do in an array, that structure is fine. Right? The basic process for adding to a hash table works like this. You take that object that you want to add, you grab its key. So you grab whatever unique identifier is for that object, you pass it to a hash function. The hash function gives you the index of where you should put that object in the hash table. Step 2 is you look at that index in your hash table and you check to see whether or not you can put that object there. If that element, if that space in the array is empty, you put it there and you're done. If it's not, then you need to handle collision because collision has occurred. Something's already there. The only method we have looked at for handling collision is open addressing using linear probing. So you simply start each index after that. So if you try to put it at spot 2 and you couldn't put it there, then you look at spot 3 and you check to see if it's empty there. If spot 3 is empty, you put it there. If not, you check spot 4 and you repeat the process until you find an open spot where you can put the object. Okay? That's it. Last thing we just went over, understand the relationship between increasing the size of the array and the effect that that has on the likelihood that collision occurs and how difficult it is to handle collision if it does occur. Right? Yes, sir?
Quick question, sorry. You said that there was the easy way and the better way. Is the better way just to increase the size?
No. It's another method altogether. And that we will cover at the beginning of our next class. Okay? All right. So remember, finish up your program. It is due, and I will see you guys next class.